reactions. And so this reaction says when an aqueous solution of sodium carbonate, so sodium and then carbonate, and you remember this is +1, -2, just gotta memorize polyatomic ions, right? We just gotta get good at those. So we need 2 NAs here, is added to nitric acid. Again, remember nitric was nitrate. And so we need an H here to balance it out. So we don't need our charges anymore. And then it says an aqueous that is added to this, and it says a gas evolves. And so when we do this, we can, this looks like a double displacement reaction, right? So our Na stays first, and our H stay first, and then our CO3. And again, remember, I'm not taking this Na here. The reason that Na is there is to balance out with carbonate, right? I don't know how many NAs are here. Remember, another way to think of it is only take the polyatomic ions with you, right? The only subscripts of polyatomic ions. This becomes Na, NO3, and then HCO3, right? But CO3 is a -2, right? +1, -1, +1, -2. So we need 2 of them. And then we need to be good at recognizing that our H2CO3 is going to further break down into H2O plus water. All right, plus CO2. Sorry, my dog is just sitting here whining next to me. I can't quite figure out why. Okay, so our whole reaction is going to be Na2CO3 plus HNO3 goes to NaNO3 plus water and CO2. And then we need to balance it, check our states. Right, so we balance it, 2 NAs, 2 NO3s, check our H's, 2 NO3s, 2 H's, we can just put a 2 here. And again, however you want to balance is fine. You'll get plenty of practice that with that on your Chem 101. Our states, this says it's an aqueous solution here, right? It says aqueous solution of acid, but all acids are aqueous anyway. Since this is in water and this is soluble, this is aqueous. Remember, water is a liquid and CO2 is a gas. And it says a gas evolves, right? So this is our reaction. All right, any questions on this one? We're good on this one? Okay, so yeah, this is just the same thing, just prettier. Exactly what we just did. Okay. So that's a gas evolving reaction. Now let's look at an acid-base reaction. Now acid-base reactions are also called neutralization reactions, but really they're just double displacement reactions. It's no different than anything else we've already done. They're just double displacement reactions. They're kind of handy, they're net ionics, because their net ionics are always the same. So their net ionic reactions are always going to be the same, which is H plus OH makes water. And you're going to see this. And this is kind of the, H plus OH makes water. And I'll show you how this works in just a second. Sorry. Okay. And I'll show you how this goes to here in just 1 second. So these are called acid-base reactions. And it's an acid, can't underline it. There we are. Acid plus a base makes salt and water. Remember, a salt is any ionic compound. We just call NaCl salt because we call it table salt because it's a salt we put on our table. But any ionic compound is actually called a salt. So an acid-base reaction, it's acid plus a base makes salt and water. But again, really, it's just a double displacement reaction. And again, our acids will ionize, form H plus, and then our bases dissociate to make OHs, and then they split. But I'll show you again, really we can just treat it just like a regular double displacement reaction. So let's try this one. So if we have nitric acid and calcium hydroxide, and we want the molecular, ionic, and net ionic. Okay, so I'm going to do this one, and then you're going to try some on your own. Okay, so nitric acid, HNO3, which hopefully we're ready because that's what our quiz is on today, and calcium hydroxide, right? +2 hydroxide is -1, so we need 2 of them, which again, that's what our quiz is on today, so hopefully we're good with this. Now, treat this just like a regular double displacement reaction. Hold on 1 second. Sorry, my dog's going nuts. So the H stays first, and the Ca stays first, and then we just switch these two, right? So our OH, again, remember, this 2, the only reason that 2 is here is because this is a +2 and this is a -1. So we need 2 of those. So the only reason that 2 is here is to balance out Ca. I don't know how many OHs I'm going to need over here. So I don't take the subscripts. You only take the subscript if it's part of a polyatomic ion, right? So this OH goes here. And now I will take this 3 because it's part of a polyatomic ion. Only take the subscripts if they're part of a polyatomic ion. Now we can see that this is HOH. That's the same thing as H2O. So if we look at our formula, an acid plus a base makes, this is our salt and water. Acid plus a base makes salt and water, but really just a double displacement reaction. It's just a special one. So we call these neutralizations our acid-base reactions, but really they're the same. Okay, so that's our, and I'm going to just leave it HOH so you can kind of see when you balance it. And so then, actually, I'm just going to change to water because actually, I think it's easier to see with water, but either or. So then we balance this and you end up with, there's 2 H's, 2 H's. Now we have 2 H's, 6 O's, and then you end up with 2 waters. And again, you can balance this a long way, but we'll practice, lots of practice on balancing on your Chem 101. And then, oh, I didn't really leave enough room for states here. This is aqueous. This is aqueous. It says aqueous calcium hydroxide. So I know I don't have to worry about looking it up. This is a liquid and all nitrates are soluble. So I'm good. Okay, so now remember, I always say, put a box around the thing that's not a solid. I mean, that's not an aqueous. Break everything else up that's aqueous. I'm not going to put the states here. I'm just going to put the charges. Everything that doesn't have a state is aqueous, okay? So this becomes 2 H pluses plus, so 2 H's, 2 NO3s, 2 NO3 minuses, plus Ca 2 plus 2 OH minuses. Those 2, don't break apart the box, plus Ca plus 2 NO3 minus, right? This is our molecular equation. This is our complete ionic. And the next step we do is we cross off everything that's exactly the same on both sides. So we look on both sides. So I have a Ca, 2 NO3 minuses, 2 NO3 minuses, and then I write down what's left. So I have 2 H pluses, and I'll put the states in here because I have plenty of room, plus 2 OH minuses, goes to 2 H2Os. And then when we write our equations, right, when we balance an equation, we keep them as simple as possible. Since these are all 2's, we just cross them out. So it's H plus OH minus goes to H2O. Okay, so a nice thing, all acid-base reactions have the same net ionic equation. They're always H plus OH goes to water. It's lovely, right? So it's a little shortcut. Like if I said, hey, what's the net ionic equation? And you're like, oh, that's an acid-base reaction. It's H plus OH goes to H2O, right? It's the same thing every single time. And so you'll see I wrote this over here. The net ionic equation is always this. right? Oops. Okay, so now I'm going to have you try these two, and then we're going to go over them together. So these are both just, again, acid-base reactions or double displacement. So try these, and then we're going to go over them in just a minute. Now, if you're watching this now or later, it's really important you try this on your paper, because this is what you're going to be doing on your quiz on Tuesday, right, when you come in to lab. Okay, so try this, and then we'll go over it in just a minute. Okay, let's go over this one. So again, treat it just like a double displacement reaction. And so when we look at this, we have our ions, and we get HCl plus BOH makes water and BaCl2. There's our water and our salt. And then of course, we have to balance it. And we end up with 2 HCl's and 2 waters. Again, we'll do the next one. H stays first, this R stays first. The OH goes here, SO4 goes here. Then we have to make sure we balance the reaction, balance our charges, and we end up with our states. Here we are with just 2 waters. Again, we treat these just like double displacement reactions. So just like double displacement reactions. Okay, so that's the end of our chemical reactions review. So just a reminder for your quiz today, it's on elements and compounds and atomic theory. Your quiz on Tuesday is what we've lectured on during this module, like the mole, aqueous solutions, and chemical reactions up until this. The next part we're going to do is quantities in chemical reactions. And we won't quite finish all of this today. So I'm not going to put this on your quiz for Tuesday because I want you to have more time than this to review for it. So I just want to quickly show you what I've done for this. So let me just go to and share my screen really quickly. There you are. So if we go to homework, here's your mole, aqueous solution, chemical reactions, stoichiometry. So when you see this homework right here, you're going to notice that all of the stuff your quiz is on, and I'm going to tell you through what number it is as soon as I go down, is all at the top, and the stoichiometry is all at the bottom. There's a lot of questions, so I've got to keep going here. See, here's balance, net reactions, net ionic, right? Complete ionic, everything we just did today. The precipitate, right? Here's all of these. Predict the products. There's a molarity question, not a precipitate, not electrolyte. See, everything we've been doing through in lectures right here. Spectator ion. So it looks like through number 85. So your quiz is on
Professor?
Go ahead.
Are we supposed to be seeing anything, or are we just listening?
Oh, you can't see this? Sorry. That's so weird. I clicked it. Oh, wait, let me try again. All right, can you see it now? Sorry, thank you. Can you see it now?
Yes, thank you.
Okay, perfect. So when you go through your homework, you're going to see 1 through 85 is what we've done, and the rest of it is stoichiometry. So I'm not going to put stoichiometry on your quiz for Tuesday because we won't quite finish it today. So just letting you know that your quiz is on numbers 1 through 85 in your homework, and I'll put that in the announcements too. But 85 through, this is all stoichiometry. You should still do it. I'm just letting you know that your quiz won't be on that. You won't be tested on that till your exam. So make sure you have that done before your quiz, 1 through 85, because you'll see your quiz, your homework's not due till the day after your quiz, just because we won't get there. We won't finish it until Tuesday during lecture. So it's not due till Wednesday. And again, you'll see that in the announcements. So your quiz is on through what we just did right now in lecture. That's what your quiz is up to. And in your Chem 101, that's through problem number 85. And so I pinned those to the top. So everyone's 1 through 85 might not be the same, but they are all the stuff they're either the mole, aqueous solutions, or chemical reactions. So that's in your numbers 1 through 85. Okay, and again, I'll put this in your announcements too. So let me make sure that my screen changes this time. Usually I triple check. Let me just check again. Okay, yes, you can see this. Okay, so quantities in chemical reactions. So this is just using balanced chemical equations to do our stoichiometry. So we should have done this a ton in Chem 209. We're just going to do more of these. And it's just going to be a little bit more work, but we're going to practice with these. And this is stoichiometry. So it's using balanced chemical equations to find our answers. But really, it's just adding one more piece to our unit conversions. It's just one little piece, and those are our mole ratios. So for example, if we look at this problem, we look at what we have. So it says, what volume of a 0.105 molar KCl is required to completely react with this volume and this molarity of PbNO3? Now, remember what we talked about when our dilutions, when you see this of, that means, again, these guys stick together. Now, it's not a dilution problem, but when you see that of, it's kind of like, okay, those are going to stick together. So when we look at what we have three things, and we have our balanced chemical equation. Now, I always tell people, when you have a balanced chemical equation, use the balanced chemical equation, right? It's like a roadmap. So if we look here, we have this many liters of this molarity of this PbNO3, which I don't really have enough room to write this, but these two are both PbNO3, and 0.15 molar is KCl. So see there, I'm just going to try and write this here. I have 0.15 liters of this, and I have 0.175 molarity. So this is really all we need to solve our reaction here. I'm just going to write this over because it's driving me crazy. So 2 KCl's plus PbNO3 2 goes to PbCl2 plus 2 KNO3s. Okay, so we have 0.15 molar of this, and we have 0.15 liters of this, and 0.175 molars of this. And the question is, what volume of this? So we want liters of this. KCl. So when we're doing this problem, you can see they're giving us more information about this PbNO3 than they are about this KCl, right? So they're giving us more information about this one. And so whenever they're giving us something, but asking for something else, we're gonna have to do a mole ratio. Now, what's the mole ratio we're gonna have to do here? It's gonna be between PbNO3 and KCl, because they're giving us information about this, but asking for this. So somewhere in this problem, we're going to be using this mole ratio. 1 mole of PbNO3 2 over 2 moles of KCl. Or it could be 2 moles of KCl over 1 mole of PbNO3. Somewhere we have to use this mole ratio because we have something and we want something else. This is the only new part for this entire thing of stoichiometry. It's just the idea of mole ratio. It's one more little step. That's it. Everything else we've already done. So I need to get to moles. So I think to myself, well, is there any way I can get to moles here? Now we remember this molarity means 0.175 moles over 1 liter. There's a moles. Also, you can remember this. Molarity is moles over liters. So therefore, molarity times liters equals moles. What does that mean? If you have a molarity and you have a volume, you can get to moles. Well, look at this. We've got a molarity, we've got a volume, we can get to moles. Now, how do you get to moles? You can absolutely, if you want to use that formula, absolutely, but you don't have to. You can just use unit conversion. Now, what do I mean by unit conversions? So if I have liters and molarity, remembering that molarity is 2 units. And again, if you have a choice to start with 1 unit or 2, always start with 1. Always, always, always. If you have a choice to start with something that has 2 units, like molarity, or 1 unit, like liters, choose the 1 unit. So if we do that, we have 0.15 liters of PbNO3, which I'll put over here. So I'm going to put 1 liter over or under 0.175 moles of PbNO3. All right, this is our volume. This is our molarity. So I just did this exact same thing, but now look, my units cancel. And now I've got my moles, so I can use my mole-mole ratio, right? The whole goal was, remember, we knew we had to use one of these somewhere because we needed to convert between these two. The only way you can do that is to use your balanced chemical equation. So now which one am I going to use? Well, I know I want PbNO3 on the bottom. Why? Because I want to cross off these units. So I'm going to choose the one that has PbNO3 on the bottom. So 1 mole of PbNO3 to 2 moles of KCl. And again, where did I get that to? Right here from our balanced chemical equation.
Professor, is the 0.15 liters, is that in the beginning? Is that from the PbNO3?
Yes.
Okay.
Great question. Yeah. So you see here, this right here, this 0.15 liters of 0.1705. So I put that right here in my really horrible handwriting. So I just transferred this down here. Yeah. So great question. Yes. And again, let me just put this here. This was PbNO3. Okay, so now we have moles of KCl. Right, this is our mole ratio. From, I don't know why things keep disappearing on my screen. Ratio, balanced equation. That's where we got this. Now, the question was, we want to get 2 liters of KCl. So you're like, I don't know how I'm going to get 2 liters KCl. I do know I need to get moles of KCl on the bottom. Why do I need moles of KCl on the bottom? Because I don't want them and I need to cross them out. So then I look, is anything up here given that can help me with that? Oh, yeah. 0.15 moles of KCl in 1 liter. That's the definition of molarity, right? So that means I'm going to put the moles on the bottom and the liter. Sorry, my computer's going crazy today. On the top, moles KCl, moles KCl. And so again, this was molarity. So when we look at this problem that I just did here, this is old. We did that last week with molarity. This again is old. We did this last week with molarity. This is the only new piece. Sometimes people get really confused with stoichiometry, but we have to remember we're really only introducing one new piece here, and it's this mole ratio. Because if we have something and we want something else, we have to do a mole ratio in between. So then in our calculators, we would put 0.15 times 2 divided by 0.15, which makes it, oh, I forgot the 0.175 there, I didn't see that, times 0.175, the entire top divided by the entire bottom. All right, so I think I have all this neater here for you. Or I'm rewriting this whole thing again, which I guess I'm rewriting the whole thing again because, oh no, here it is. I was like, wait, nope. I erased it, so we'll write it again. So we get, I'm just gonna rewrite this really quickly this time. So we have 0.15 liters, and then 1 liter, 0.175 moles of PbNO3. See, sometimes I don't do my keys when I think I do. 1 mole of PbNO3 to 2 moles of KCl, and then 1 mole of KCl 0.15 moles in 1 liter. All right, so I'll just use my phone for my calculator. Times 2 times 0.175 divided by 0.15. So we end up with 0.35 liters. But when we look at this, 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So again, this is molarity. This is molarity. We did those last week. This is the mole ratio. This is the new piece that we put it together. Okay, so we're gonna try another one of those. I really need to leave myself more room to write, but I'm gonna try and write neater. Okay, so if we look at this problem, how many grams of oxygen can be made from the decomposition of 100 grams of PbO2? So in this case, we have 100 grams of this. We want this, so we're gonna go from here to here. So again, when you see the balanced equation, you should go, uh-oh, I'm doing a mole ratio. Like that should be like your first thing. It's like, oh, doing a mole ratio here because you see the balanced equation. What's the mole ratio we're gonna do? They gave us PbO2, they wanted O2. So our mole ratio somewhere in this problem is gonna be this. 2 moles of PbO2 to 1 mole of O2. Now it might be written like this, or it might be upside down. It's one of those two. I don't know. All I know is somewhere in this problem, I'm using that, which means I've got to get to moles because the only way you can do a mole ratio is if you have moles. Okay, so here's what we're given. I think I have molar masses here. I do. Molar masses, very important. All right, so when we do this one, well, we only have one number, so it's much easier to figure out where to start with this one, right? Because there is only one number. So 100 grams of PbO2. And again, my goal here is I need to get to moles because I have to use this somewhere, which means I have to get to moles. I know how to go from grams to moles, right? Molar mass. We've done that. Give you the molar mass now. So there's 239.2 grams of PbO2 in 1 mole of PbO2. Aha, look, moles of PbO2. I can use my mole ratio now, right? The whole goal, get to the mole ratio. What's going to go on the bottom? PbO2. Why? Because I want to get rid of the unit. So that means that the top is here, and I flip this, the bottom goes here. Again, why? I need to cross this out. Now I have moles of O2. The question asked for grams, right? I want grams of O2. Oh, again, we know how to go from moles to grams. In 1 mole of O2, the molar mass is 32 grams of O2. Again, moles goes on the bottom because I want to get rid of my units, right? The whole goal, we want to get rid of the units. So the question, will molar masses be given on the quiz? By the time you get to this one, most likely. Most likely, I will give you the molar masses just because at this, for your next quiz, quiz number 2, you're going to have to add some molar masses because I want to make sure you can, not for quiz 2, for quiz 3, you're going to have to add molar masses. But when you get to exam 1, I might ask you 1 molar mass question, and the rest of the time for the rest of the semester, I will give you molar masses because it just becomes annoying to add everything. And kind of a, I don't want to say it's a time waster, but it is annoying. Okay, so when we do this, we get, let's check our sig figs out, 4 sig figs. And we get 6.689 grams of O2. Now, this molar mass from the periodic table. This molar mass, periodic table. This is our mole ratio. This is the only new thing. This is old. This is old. This is new. So all the mole ratios are doing is bringing things we already knew how to do and joining them together, right? So this is the only new piece to what we just did. The rest of it is just going from grams to moles or moles to grams, which we know how to use the periodic table. So a lot of times the stoichiometry people are like, oh, that's so long, but really it's just, you need to get to the mole ratio. That's all we're doing is trying to get to that mole ratio. Okay. Oh, look, of course I have this one on here for you, but I didn't have the last one. All right, here's the solution for this one. Okay, any questions on this one? Okay, we're about to lift it up a couple levels here. Okay, now, the limiting reactant. So when we're doing a reaction, there's always a limiting reactant, meaning one reactant runs out before the other one. That's what our limiting reactant is. It's the one we run out of first. The other one is called the excess because we have extra of it. When we get our limiting reactant, we can use or find our limiting reactant is our theoretical yield. So a lot of times people are like, I don't know which one my theoretical yield is. This is a theoretical yield. This is a theoretical yield. All of those are theoretical. So what we've been doing, theoretical yields. Theoretical yield is when you look at the periodic table or do a mole-mole ratio, that's a theoretical yield. So theoretical yield is what we've already been doing. So it's what we've already been doing. It's different than the actual yield. The actual yield is the one we get in lab. So in lab, we're going to be using these theoretical yields and actual yields all the time. The actual yield is the one you actually get in lab, right? So what you actually mix the reactions and what did you actually get? That's the actual yield. And we use the theoretical yield and the actual yield to get our percent yield. So again, this is the one you actually get in lab when you mix the chemicals. This is the one when if you use your periodic table or a mole ratio or a molar mass, you're doing your theoretical yield. Okay, so we're going to try a problem that uses all three in one. So here's our example. When 28.6 kilograms of carbon are allowed to react with 88.2 kilograms of TiO2 in the reaction below, 42.8 kilograms of Ti are obtained. Find the limiting reactant, the theoretical yield, and the percent yield. Okay, so a lot of times people see this and they're like, whoa, wait, what? All right, let's look at what we've got. Again, if you got a balanced chemical equation, use the balanced chemical equation. So it says when you have 28.6 kilograms of C, okay, so it's 28.6 kilograms of this, and it reacts with 88.2 kilograms of this, it says we get 42.8 kilograms of this. And we want our limiting reactant, our theoretical yield, and our percent yield. Okay, so remember, percent yield, I always think of percent yield is the word, it says at. At, that's an A, by the way. I mean, just use the capital A. At actual yield over theoretical yield. Some people say big over little. Oh, that's definitely not true. Most of the time it's true, but sometimes it's not. Actual over theoretical. Remember, actual yield is what you actually get. Theoretical yield is what you actually get. Remember, these are what you get. So these are both products. A lot of times I see people and they put a reactant in here. No, it's the yield. These have to be products, right? And so when we look at this, it says that 42.8 are obtained. That must be our actual yield. Because that means when we actually mixed this and this, and we put it in a container and we let it react, we made 42.8 kilograms, right? By the way, your actual yield is pretty much always given to you unless you're in lab. They have to tell you because you can't mix it in paper, right? You don't know what you're going to get when you actually mix it together. So in a problem, they pretty much always give you the actual yield. The one you're finding is going to be the theoretical yield. So this is our actual yield. So that means we need to figure out our theoretical yield. And we have our actual yield. Now, that means when we mix this and this together, one of them runs out first. That's going to be our limiting reactant. We're not going to use exactly this much and exactly this much. Yeah, that like never happens. It never really happens. One of them gets used up first. We need to figure out which one gets used up first. Okay, so there are so many different ways to do this problem. I'm just going to show you the way that I found that it seems the easiest for people conceptually. But if you have a different way that you've already learned how to do limiting reactants, as long as I can follow your work, I'm okay with whatever way you do your limiting reactants. So again, what do we have? We have 26.8 kilograms of this and 88.2 kilograms of this. And I'm not really going to worry about this one because this one, that's my actual yield. So when I do my percent yield, remember it's at actual or theoretical, this one's going to be 42.8. I'm looking for this right now. I'm looking for that bottom number, actual over theoretical. Okay, so again, what I'm going to do here, since I know I'm looking for TI, what I'm going to do, and again, so many different ways to do this problem. I'm going to take this and say, hey, if I used all of my 88.2 kilograms, how much TI could I make? Okay, and then I'm going to go, hey, if I use all of my 28.6 kilograms, how much TI can I make? And the reason I'm choosing TI is because that's what we're going towards. So I call this like two birds, one stone, right? You kind of get two, it's sometimes this way is a little bit longer, but in the end, you only have to do 2 problems versus 3. But again, if you learned a different way to do this, go ahead, do this. Okay, so I'm gonna do 88.2 kilograms of TiO2, and I'm going to convert it to kilograms of TI. Again, why did I choose kilograms of TI? Because that's what my actual yield is in, and that's what I'm going to go to. Okay, so can't do a thing with kilograms. Not useful for me. In 1 kilogram, there's 1,000 grams. Got that one down. And this is TiO2. Now, I know for sure I'm going to have a mole ratio here. And what is my mole ratio going to be? It's going to be 1 mole of TiO2 to 1 mole of Ti, right? Or it might be 1 mole of Ti over 1 mole of TiO2. It's one of those two because this is a 1, this is a 1. Okay, I'm using that mole ratio. What does that mean? I got to get to moles. When you see that balanced chemical equation, you think, I have to use my mole ratio. So it means I got to get to moles. And so I added the molar mass for you. The molar mass is 79.87 grams of TiO2 in 1 mole of TiO2. I should put this here just to be extra clear. Grams, TiO2, TiO2. Always got to have our units, right? So then grams cancels out with grams. Okay, look, I'm at moles, right? My whole goal here, get to my mole ratio. So if I get to my mole ratio, then I can get to my product. So I can see I'm going to use this one. Why? Because I want moles of TiO2 on the bottom. So that means moles of TiO2 on the top. Okay. Now, I got moles to TI. I want to go to kilograms. Well, in 1 mole of TI, go to grams, which is moles. So this is 47.87 grams of TI. I have grams, I can go to kilograms. There's 1,000 grams of TI in 1 kilogram of TI. Grams, grams, I end up with kilograms. Now, this is like, whoa, it's long, but think of this. This is just a metric conversion. This is just using the periodic table. This is our mole ratio. This is the new piece. This is just the periodic table. And this is just a metric conversion. So it's just using all of those pieces and we're putting them together. How do you know which piece to put where? Follow the units. Okay, I don't even know what you get here. I'm just gonna go, I'm gonna do the next one and I'll come back and put it in my calculator later. So our next one, so actually I'll put this in the calculator just so I can explain using numbers. Times 1,000 times 47.87 divided by, open parentheses, 79.87 times 1,000. Actually, I could have just left 1,000 out. So I got 52, sig figs are all 3, 52.9 kilograms of TI. Okay, so what's this mean? So what did I just do, right? So this is saying that if we use 88.2 kilograms of TiO2, we can make, I'll do this from the top here, we can make 52.9 kilograms of TI. So if we use all 82, use all the 88.2 kilograms up, we can make 52.9 kilograms. Now, is that real or not? I don't know, we gotta see. So what I do, the exact same thing with the next one. And again, there's so many different ways. You could go to moles, you could do comparison. I'm just gonna go both of them to TI. So our next one, we have 28.6 kilograms of carbon. And again, this first piece is going to be exactly the same because I can't do anything with kilograms. In 1 kilogram of carbon, there's 1,000 grams of carbon, units. Same thing, molar mass, using our periodic table, there's 12.01 grams of carbon, right? Let's say I didn't know to use my molar mass. Well, I just put grams on the bottom because I need to get rid of them. And I think, how can I get to grams? Oh, the periodic table is grams per mole in 1 mole of carbon. Now remember, whenever you look at that periodic table, the number that you get, so here's carbon, this means 12.01 grams of carbon in 1 mole of carbon. It's always over or under 1 mole. That is what this number means, 12.01 grams per 1 mole. If you look at the periodic table, the only choice is the number 1 on the other side. No other choices. The only time you can have more than 1 mole is if you're looking at a balanced chemical equation. That's it. That's the only time. So now we know we want moles of carbon on the bottom. And we're like, oh yeah, mole ratio. What's our mole ratio? So right now we're trying to go from carbon, titanium. There's 2 carbons to 1 TI. Moles, moles, grams, grams. And now this one, like the next 2 boxes are exactly the same, right? 1 mole of TI is 47.87 grams. Here's where it's like a little bit of redundant and there's like a little bit of extra. But again, it brings you straight to your answer And so that's kind of why I like doing it this way, but you don't have to do it this way if you want to do it a different way. Okay, so I put this in my calculator, 28.6 times 47.87 by 12.01 plus 2. I get 56 point, how many sig pigs? 3. So my calculator says 56.997. So I need to round that to 57.0 kilograms, right? With 3 sig pigs. Okay. Okay, so what did I just do? So if I use all 28.6 kilograms, I can make 57 kilograms of TI. Now, both of these aren't real, right? One of these is my limiting reactant. So let's look at this for a second here. How can you tell which one is your limiting reactant? In short, it's the one that's smaller. But what does that even mean? So we use, let's do a nice light blue. If we use 88.2 kilograms of TiO2, we make 52.9 kilograms of TI. We use all 28.6 kilograms of carbon, we make 57. Okay, so we need to think about that. If I use all of this, I make 52.9 kilograms of TI. So that means after all of my TiO2 is used, it's all gone now. I used all 88.2 grams. I made 52.9 kilograms of TI. Well, that means after I've made 52.9 kilograms, I've got no TiO2 left. So I could have never gotten to 57 because there's no reaction, because this is all gone. This is my limiting reactant. It's gone. After I made 52.9 kilograms of TI, I didn't have any more of my TiO2 left. See, it's gone. The reaction stops. This is my limiting reactant, which means I did all this work. It's imaginary. It never even happened. So again, this is a little bit longer of a way to do it, but in the end, you just know that your limiting reactant is the one you made less of. Now, a lot of times, this question says, what's the limiting reactant? I get people telling me this is my limiting reactant. Okay, it's a reactant. It must be a reactant. There are only 2 choices here for a limiting reactant. The limiting reactant is either TiO2, which is a reactant, or carbon, which is a reactant. This is a product. This is a product. The limiting reactant must be a reactant, right? So if this was a multiple choice and it said like, which one is the limiting reactant? And it was like A, B, C, D. Well, it's definitely not these 2 because those are products. Limiting reactants must be reactants. So when you do it this way, your limiting reactant is the one you start with. So TiO2 is our limiting reactant. What is our theoretical yield? This is why this way is kind of nice. It's the one thing you ended with, right? It's the smallest one. See, it's 57 or 52. It's the smaller one. And that's your theoretical yield, not limiting reactant, right? Theoretical yield. This means if we used all of our TiO2 and everything went perfectly, this is how much we should get. Now, does this ever happen? No, right? We don't ever actually get this, but this is if everything went perfect, like everything went absolutely perfect. We should get 52.9 grams of our titanium. So now let's see how far off we were from perfect. So now when we do our yield, our percent yield, this is our theoretical yield. That's what goes on the bottom here. So if we do our percent yield, remember it's actual over theoretical. The actual has to be given to you because we didn't do this in lab. So we decided that one was 42.8 kilograms of TI. Our theoretical is whenever you use your periodic table, whenever we use a mole ratio, those are always theoretical yields. 52.9 kilograms of TI times 100. So 42.8 divided by 52.9 times 100. I got 80.9%. So that means I got about 81% yield. That's actually pretty good, right? That's my percent yield. Okay, so again, when you have a limiting reactant, how do you know, first of all, that you have to do a limiting reactant? Let's do this in a different color, yellow. If they give you information about both reactants, you have to find out which one gets used up first. If they only give you one, then you don't have to worry about it. But if they give you information about both, you have to figure out which one gets used up first. That's the limiting reactant. And our limiting reactant, this is the only new piece right here. The rest of this is all old. We've done this a bunch now, right? Our mole ratio, our percent yield, again, this is our actual yield, which is always given to you, right? This is the one. I always say if you used your calculator, that was your theoretical yield, right? The actual yield's always given to you. Okay, any question about where any of these numbers came from or how any of this works? Questions? Feeling pretty good on this? Yeah? Stoichiometry. It's actually kind of fun. Okay. So this is just what we did, and we got 80.9% yield. So, hey, we did it right with our calculator, right? Okay, so now we have another one. Oh, here, these are just all the answers, but we already just did this one. Okay, so that's percent yields, theoretical yields, limiting reactants. Now we're going to do one more thing, which is acid-base titrations. All right, so you know what? I want to do one more thing here. Just because you're going to need this, I'm going to look at how much extra or excess reactant is left over. This isn't necessarily part of our problem, but it's actually a really important skill, and I don't have one of these on here. So I want to know, so for example, if this is our limiting reactant, that means we used all of this up, right? But what if I want to know how much of this is left over? So this is our limiting, this is our excess reactant. Get it? Excess, our excess reactant. What if I want to know how much of that reactant is left over? Okay, so if you want to know excess reactant, there's really only one more step. I'm going to do this one in purple, right? Our excess reactant. What we're going to do, so how you figure out your excess reactant is you take your limiting reactant and you say, if I use all of my limiting reactant, how much of this is needed when I use all my limiting reactant? So what we do is you take your limiting reactant and you just convert it to your excess reactant. So for example, I use all 88.2 kilograms of TiO2. How much carbon is needed to do that? So I'm just going to react my TiO2 with carbon on paper. So this first part's exactly the same. 1 kilogram TiO2. Oh gosh, I'm going to rewrite that for you. And 1,000 grams of TiO2. And then same thing here, 79.87 grams of TiO2 in 1 mole of TiO2. So again, what I'm doing here is I'm going to react my limiting reactant and see how much of this is used up. So my mole ratio is going to be between those two, right? So I'm going to convert from TiO2, and I want to go to carbon. So there's 2 moles of carbon. So I'm just reacting this with this and seeing how much I need. So in 1 mole of carbon, so I'm following my units here. Carbon has to go on the bottom. There's 12.01 grams of carbon. Put that to kilograms because we're just in kilograms. Grams of carbon in 1 kilogram of carbon. So 88.2 times 2 times 12.1 by 79.87. So I got 26.5 kilograms of carbon. Okay, so what does this mean? When I use 88.2 kilograms or all of my limiting reactants, I need 26.5 kilograms of carbon. So I have 28.6 kilograms of carbon, but I don't use it all. All we use is 26.5. So if I want to know how much carbon is left over, all I need to do is take how much I started with, which was 28.6 kilograms, amount started with, and I subtract the amount we actually used, amount used. So 28.6 is how much we started with, minus 26.5 is how much we use. That means we have 2.1 kilograms, and this is the amount left over. So if they ever ask you how much excess reactant is left over, this is how you do it down here. So again, how did I figure out the amount of excess reactant left over? I figured out my limiting reactant. And then I said, if I use all of my limiting reactant, how much of my extra reactant will I have left over? So you react the two of those together, which is this mole ratio right here. And then that tells you how much we actually used. To figure out how much is left over, you take the amount you started with minus the amount you used, and that gives us the amount left over. So you're going to be doing this in Chem 101 and definitely on your exam. So I want to make sure that everybody's seen this. Any questions? I know this is a huge problem and it's kind of like maybe 3 weeks of your intro chem class all in one problem. Any questions on this one at all? It's a big question. It's a big problem. Go ahead.
Professor, obviously, like a simple question, but it's always going to be a lower amount. When you know the purple problem you just figured out, it's always going to be a lower amount that you started with.
Yes, if it's not, something went very wrong with the problem, right? So that's actually a really, really good question. What if, and I'll do this in yellow, just so you can see, like, what if this answer actually ended up being more than this? Oh, we did something wrong, right? Something wrong happened in these reactions. Yeah, so this answer should always be smaller than this number, because this is the excess reactant, meaning we should have extra left over, which means we should have used less than that number. And we did in this case use less. If it's bigger, then yes, something went wrong in these top two calculations. Yeah, great question. Like that shouldn't happen. So it should always be smaller. Okay, so just in summary, when you do limiting reactant, a fast way to do it, it's not necessarily fast, an easy way to do it is convert both of your reactants to the product they're asking for. So they gave us TiO2 and carbon. We convert both of those to Ti. So that's what we did. We converted both of those to Ti. And I just used, you could have done these to grams and then done kilograms later. That would have been fine. Convert them both to the products they're asking for. Whichever one is smaller is your limiting reactant. 52 is smaller than 57. So that's your limiting reactant, whichever one's smaller. The other one never occurred. I always say cross it off. You don't need to like black it out so you can't see it. Just cross it off so you're not tempted to ever look at it again because you're never using it again, right? Once you find that limiting reactant, that extra piece is just extra. You're never looking at it again. Then you use your limiting reactant, that's your theoretical yield. And so that's going to go on the bottom because it's theoretical yield. The actual yield is always given in the problem. It's how much you actually get in real life. And then you get your percent yield. If they ask you how much extra is left over, you always start with your limiting reactant. Always. I always say this, once you find your limiting reactant, use your limiting reactant. Always use your limiting reactant once you find it. And then you convert your limiting reactant to the other reactant to see how much of it you used. And then you subtract it from the original amount. So here's our original amount. Here's the amount we used, and that's going to give you your excess reactant. They're very long questions. Very long questions. Okay, any other questions on this one? Said it's kind of a long one. And if you're watching this later and you're like, wait, where did that number come from? Just send me a quick text and I can definitely help you with that. So someone said we have questions for all four. Yeah, this is on your exam. I would expect a question like this. Definitely no. On your quiz, there's no stoichiometry on your quiz number 3. I didn't put it on there. It's too long. But for your exam, I would definitely expect a question like this. Absolutely. Yeah, very similar to this question. I haven't made it yet, but I guarantee you this is something I would put on an exam. And you'll see in Chem 101, there's questions like this on Chem 101 too. Okay, so quickly, we're just going to talk a tiny bit about acid-base titrations. And so an acid-base titration, it's really just stoichiometry with solutions. We're going to be doing these titrations. Our last lab we do in the semester is a titration, but it's really nothing different than we've already done. It's just actually really fun because you get to turn things colors, and I'm going to show you how it works. So we have this thing called an indicator that changes colors if it's an acid or a base. And the equivalence point just means when we have the same amount of acid and base. And so how titration works, and we'll just talk about it a little bit now because we're going to talk about it in lab a ton. And we're really only going to do the calculations. So you have in here, you have a base in this thing called a burette, which we're going to be using a bunch. And you have an acid here. And in this thing, you have an indicator. The indicator, when it's an acid, is clear or colorless. I'm just going to say clear, but really colorless. But it turns pink when the acid equals the base. When the acid equals the base, see how it turns pink? You'll see it turns pink and then goes away. And then this is when we call this the equivalence point when acid equals base. And then it turns pink. It's actually probably the most fun lab we do. But what we're going to do is we're going to calculate how much acid or how much base we use. So like I said, we're not going to talk about too much about this right now because I want to show you this is literally the exact same thing we were just doing. Okay, so a titration, just think of it as an equation. And we have HCl and NaOH. And we want to know, so we have a titration of 10 milliliters of HCl with an unknown concentration that requires 12.5 milliliters of a 0.1 molar solution to reach the endpoint. What is the concentration of the HCl solution? Okay, so I'm going to put this here so I can write this down a little bit. Okay, so first of all, one thing I want you to notice. Do you see how it says HCl and NaOH? Whenever you see a problem and there's two different things in there, it's probably a good thing to note. You're going to have to write your own balanced chemical equation. Yep, they're not always going to be given to you. How do you know? Well, how would we possibly know how to go? It's asking about HCl, giving us HCl, giving us NaOH. How would we possibly know where to go if we don't have a balanced chemical equation? And we just did this. This should look like a double displacement reaction. H stays first, Na stays first. The last two switch. Look at this. This is an acid plus the base makes a salt and a water, right? So the acid-base reaction, just like we just did. And again, HOH is the same thing as water. It's nicely balanced. We're good. So now let's look. What do we have? So we have 10 milliliters of this, right? 10 milliliters of HCl. And then we have 12.54 milliliters of a 0.1 molar solution NaOH. What is the concentration? Remember, concentration means molarity. So we want the molarity of HCl. Okay, so they're giving us information about NaOH and they're giving us information about HCl. Well, that means our mole ratio will be between NaOH and HCl. So somewhere in our problem, we're using this. Where? I don't know, but we've got to use it. It's happening somewhere in this problem. So what do we start with? We've got to get to moles, which means we have to get to moles, which means we have to get to moles. We got to figure out, how do we get to moles? Well, this only gives me milliliters. That's not useful. This gives me milliliters and molarity. So remember, we just did this. If molarity is moles over liter, then molarity times liters equals moles. I have the molarity, I have a liter, milliliter, close enough. I can get to moles. So that means we're going to use this. And again, I asked the question, we can start with 2 units or we can start with 1. I choose 1. Right, so if we start with 12.54 milliliters, we have to get to liters, right? Milliliters, milligrams, none of those are helpful for us. There's 1,000 milliliters in 1 liter. Now we can use our molarity because remember, 0.1 moles of NaOH, that is 0.1 molar. That is the same exact thing. Now I can use my mole ratio. NaOH has to go on the bottom because I want to cancel it out. Cancel, cancel, which means moles of HCl needs to go on the bottom. Now remember, I want molarity of HCl. That means moles over liters. Well, if I look here, here's my moles. They give me 10 milliliters. So I can just convert this. 0. Or just because we're starting with this, 1,000 milliliters in 1 liter. You can just move your decimal place over 3, or you can put it in 0.01 liters. And then we figure out our moles here, 12.54 times 0.1 divided by 1,000, 1.254 times 10 to the negative 3. I'm not doing my sig figs till the end. This gives me 0.1254 moles HCl, just to be clear. Moles of HCl per liter, which is the same thing as 0.1254 molar HCl. So this problem really is the same as we did before. It's just the words are a little bit different, right? But it really is the same problem. Here we are with a metric conversion. Here's a metric conversion. Here's molarity. here's our mole ratio. Right? And so we just put all those in one piece. Again, how did we get from one piece to another? We followed our units through, and we wanted molarity in the end, and molarity is moles over liter. So we got our moles here, moles over our liters. And you can do this all in one step too. I just broke it up because sometimes people feel a little overwhelmed when I put it in one step.